Hello students. In today's class, we discussed about the relationship among three elastic constants. What are the three elastic constants? As we know that in the earliest classes, we discussed about three elastic constants already. What are those? First one is the Young's modulus, or modulus of elasticity. Second one is the rigidity modulus or shear modulus. Third one is the bulk modulus. First one, Young's modulus. What is meant by Young's modulus? How to define an Young's modulus? Young's modulus is defined as the ratio of linear stress to the linear strain. It is the ratio between linear stress to the linear strain. Stress by strain is the Young's modulus. And rigidity modulus. Young's modulus is denoted by capital E. And the rigidity modulus is denoted by capital G, which is defined as the ratio of shear stress to the shear strain. Shear stress divided by shear strain is called the rigidity modulus or shear modulus, which is denoted by capital G. And third one is the bulk modulus. Bulk modulus, which is denoted by K, capital K. It is the ratio of direct stress to the volumetric strain. Direct stress to the volumetric strain is the bulk modulus. These are the three elastic constants. In this class, the relation among these three elastic constants we are going to derive. First case, in case 1, relation between E and G. What is the relation between E and G? That is, E is the Young's modulus, G is the rigidity modulus or shear modulus. Let us take a diagram that is a square, which is on which the shear stress are acting. Q is the shear stress on the surfaces. A, B, C, D are the surfaces. This is the diagram. Consider an element A, B, C, D in the material of side small a subjected to pure shear. Q is the pure shear on 4 surfaces. Q is the pure shear. This is the shear force, shear stress. AB and CD, or the clockwise shear stress. AD on the surfaces AD and CB, anti-clockwise shear stresses automatically developed. These are called the complementary shear stresses. When we apply the shear force on the 2 surfaces, the shear force on the perpendicular surfaces automatically develops by resisting the material against the rotation. So subjected to pure shear, Q is the pure shear as shown in figure. AEC D, AEC dash and D is the deformed shape after applying the shear force or shear stress. Deformed shape due to shear Q. Drop a perpendicular FB. Observe this diagram first of all. A, B, C, D is the initial shape before applying the shear force. A, E, C dash and D is the deformed shape after applying the shear force. Like this, it is looks like a parallelogram after applying the load on the surfaces. If we apply the load, for example, this is the surface. If we apply the load on the surfaces, it will be deformed like this as a parallelogram, and angular deformation takes place. Some angle will be formed after applying the load. That angular deformation is called the shear strain, which is denoted by phi. Here, angular deformation, this much of angle will be deformed by applying the shear force on the surfaces. Let us take a perpendicular line, drop a perpendicular to perpendicular FB. This is the F and B. This is the perpendicular line onto the line DE. If we draw a perpendicular line FB onto the line DE, let phi be the shear strain and G is the rigidity modulus. Capital G is the modulus of rigidity or rigidity modulus. Now strain diagonal BD. What is the strain by applying the load? We are going to analyze the strain. What is the deformation, change in length of the diagonal BD here? What is the change in length of the diagonal BD? The BD becomes, after applying the load, the BD becomes DE. Clear? The DB diagonal becomes DE after the applying load. That means it will be extended somewhat. How much extended? That is the strain in diagonal BD is equal to how much extended? That is the initial final length is DE, diagonal DE. Initial length is DB. Oh, sorry, D. 1 minute. The initial length is DB, the final length is DE. How much extended change in length of the diagonal? By drawing a perpendicular line FB onto the line DE, this is much of length is increasing the diagonal BD, isn't it? So change in length of the diagonal is DE, the final length, minus initial length. Initial length is dB. Initial length is dB. DE minus dB by TF. Sorry, this is the wrong. Change in length is EF. That is the change in length is the EF. DE minus DF. DE minus DF is the change in length. This is much of the change in length. Divided by initial length is, what is the initial length? Initial length is DF. DE minus DF is the change in length, because DE is the extended length, that is the final length after the extension, minus DF. If we subtract the DF from the DE, then we can get the change in length of the diagonal. Change in length of the diagonal. This is EF. Divided by what is the initial length? Initial length is dB. That is equal to dF. These two are the equal. By draw the perpendicular line, the dB is equal to dF. These are the two lengths are equal. The extended length is EF. So initial length dB in place of dB, I written here dF. dF is the initial length. So by changing that, DE minus DF is equal to EF. This much of length is increasing by the load applying on the surfaces. Divided by initial length is dB. So change in length by original length of the diagonal is strain in the diagonal BD. Clear? So EF, what is the EF? EF as it is in the numerator, and denominator dB is there. dB, what is the dB? dB is the initial length. That is the actual diagonal of the element. dB in place of dB, we can write in terms of AB. In terms of AB, if we write the AB, this angle is, how much this angle? If we draw the diagonal of a square, how much this angle is? 45. So let us take the 45, cos 45, cos 45, this is a 45 degrees. Cos, if we take the cos 45, adjacent side is AB, hypotenuse is DB. So cos 45 is equal to AB by DB. Therefore, DB is equal to AB by cos 45. AB by cos 45 is DB. In place of DB, we can replace AB by cos 45. Cos 45 is the 1 by root 2, isn't it? 1 by root 2. We can write 1 by root 2. If root 2 numerator then it can be write as root 2 AB. In place of DB, we can write as root 2 AB. So root 2 into AB, EF by root 2 into AB. Clear? This is the final formula for the strain in diagonal BD, EF by AB into root. Since angle of the angular deformation is very small, ఇది మన లోడ్ అప్లై చేసినప్పుడు ఈ యాంగులర్ డిఫార్మేషన్ అనేది చాలా తక్కువగా ఉంటుంది. దెన్ వీ కెన్ అస్యూమ్ దట్ ఆఫ్టర్ డిఫార్మేషన్ ఈజ్ ఆల్సో టేక్ ఇట్ యాజ్ దిస్ ఈజ్ 45 degrees. So we can take it as angle AED is also 45. Therefore, BEF is 45. Angle BEF, where is B? E EF or BED. You can write as BEF or BED. 45 angle 45 degrees. Hence, EF, that is the change in length. EF is equal to how much we can write? How to write? By taking the triangle BEF. BEF. This is a BEF cos 45. This is the 45. If we take the cos 45, that is the adjacent side EF, our hypotenuse is EB. So EF by EB. Therefore, EF is equal to EB or BE cos 45. EF is equal to BE cos 45. It becomes EF can be written as BE cos 45. Therefore, strain in diagonal in place of EF, we can write BE cos 45. BE cos 45 in the numerator. In the denominator, AB root 2. BE cos 45 in place of BE, we can replace that BE. What is the BE? BE means this is the extended length, isn't it? This is the, after deformation, the B becomes E. So if we take the tan phi is equal to, what is the tan phi? If we take the triangle ABE, from the triangle ABE, tan 45 is equal to, sorry, tan phi is equal to opposite side divided by adjacent side. What is the opposite side here? BA divided by adjacent side is AB. AB is means side of the square. What is the side of the square? A. So tan phi is equal to BE by A. So BE is equal to A tan 45. So BE can be written as, in place of BE, A tan phi into cos 45 divided by AB means this is the side of the square. AB can be replaced by small a, side of the square, A root 2. Dear students, a simple explanation here. Mathematical equations, all of the mathematical equation. Strain in the diagonal, we are finding the strain in the diagonal here. Strain in the diagonal is change in length of the diagonal divided by original length of the diagonal. Change in length of the diagonal will becomes finally A tan phi cos 45 divided by initial length of the diagonal is A root 2. Clear? So here cos 45, here cos 45 again 1 by root 2, 1 by root 2, root 2 into root 2, 2. So off, A cancel, off tan phi, it becomes off tan phi. If the angle is very small, that is the deformation is very small, tan phi can be written as phi. So therefore, final equation, strain in the diagonal is phi by 2 or off into phi. Phi is the, this is the phi means it is the angular deformation of the member or shear strain. It is also called shear strain. Therefore, strain in the diagonal is equal to half of the shear strain. Clear up to this? Next, strain in the diagonal is also is equal to 1 by 2. In place of phi, we can write as, what is the phi? Phi is the shear strain already. We told that. Phi shear strain. What is the definition of the rigidity modulus? Rigidity modulus is the ratio of shear stress, that is the Q. In some books, it is represented by tau. This is the tau. It is the shear stress, or Q in some books, it is represented by small q. Shear stress by shear strain. Shear stress by shear strain is the rigidity modulus. Linear stress by linear strain is the Young's modulus. Shear stress by shear strain is the rigidity modulus. From this equation, phi can be written as Q by G. So, in place of phi, the phi can be replaced by Q by G. So, since phi is equal to Q by G from this equation, phi equal to Q by G from the rigidity modulus definition. Clear, students? Now we know that the above pure shear gives rise to axial tensile stress equal to Q. ఎప్పుడైతే మనం సర్ఫేసెస్ మీద షియర్ స్ట్రెస్ అప్లై చేస్తామో, ప్యూర్ షియర్ అప్లై చేస్తామో, డయాగ్నల్ పైన కూడా సేమ్ స్ట్రెస్ డెవలప్ అవుతుంది, దట్ ఈస్ క్యూ. Same stress Q develop అవుతుంది in the diagonal direction dB. And axial compressive stress, once again go to problem. So whenever we apply the shear stress on the surfaces, it deforms like a AEC-D, isn't it? So after deformation AEC-D, on the diagonal, due to these two shear stresses, due to these two shear stresses on the surfaces AB and BC, the resultant stress acting in this direction, the resultant stress or the resultant force acting in this direction. One minute. Resultant of these two shear forces or shear stress on the diagonal, the resultant in this direction, Q itself. Resultant is also Q itself. A resultant of these two shear forces or shear stresses, the resultant force on the diagonal in this direction, this is also Q itself. So by applying the shear stress on the surfaces, on the diagonal, the axial stresses acting, that is tensile stresses acting on the diagonal, and resultant of these two, this is Q and this Q, resultant of these two shear forces, the resultant force acting in this direction Q itself, and the resultant of another two surfaces on the AB surface and the AD surface, resultant of these two, the shear force acting on the diagonal AC in inward direction. So diagonal AC paina act the inward forces, that is the compressive forces, diagonal BD paina act the tensile forces. Due to these two forces, due to force acting on the diagonal AC, that is diagonal AC is trying to compress. Due to compression on the diagonal AC, the BD diagonal will be extended. At the same time, the force acting on the diagonal B is also the diagonal BD extended. Clear, students? These are diagonal BD extended by two reasons. The force acting on the diagonal BD, tensile force acting on the diagonal BD, and the compressive force acting on the diagonal AC. Due to these two forces, the diagonal BD will be extended. So here I written that we know the shear gives rise to axial tensile stress equal to Q in the diagonal direction of DB, and axial compressive stress equal to Q again at right angles to it. Right angles means perpendicular line. That means that is the diagonal AC, on the diagonal AC. These two stresses causes tensile strain along the diagonal DB. ఈ రెండు కేసెస్ వల్ల diagonal DB అనేది extend అవుతుంది. So tensile strain along the diagonal DB. What is the tensile strain along the DB? That is the strain in the DB, strain in the diagonal DB is equal to, we can write as, due to two reasons, tensile strain is equal to tensile stress by Young's modulus. Tensile stress by Young's modulus. Why the Young's modulus is taken here? Because we are going to calculate the tensile strain, that is strain in DB, linear strain in the DB is equal to linear stress by Young's modulus. Here linear stress is also equal to shear stress acting on the surfaces. So therefore, I retain the linear stress is also notated by Q here. Linear stress is equal to, linear stress on the diagonal is equal to shear stress on the surfaces. Therefore, linear stress is equal to Q by E. Strain is equal to Q by E. This is one of the reason. Plus, another reason is the stress acting on the diagonal AC is also causes to increase the length of diagonal BD. So, diagonal BD is the lateral strain to the diagonal AC. That is, the diagonal BD is the lateral direction to the it becomes lateral direction to the diagonal AC. So from the Poisson's ratio definition, the lateral strain is equal to Poisson's ratio into linear stress along the AC. So Poisson's ratio mu into Q by E. From these two equations, Q by E it is as a common. Q by E common, then 1 plus mu. It can be written as 1 plus mu, equation 2. From the equation 1, what is the equation 1? Strain in the diagonal BD is equal to half into Q by G. Already we derived. So in the second equation, the strain along the diagonal DB, same strain in the diagonal BD is equal to Q by into 1 plus mu. From these two equations, half into Q by G is equal to Q by E into 1 plus mu. So from this Q cancel, from this equation E taken, it is a left hand side into the numerator and 2g into the right hand side into the numerator. So E is equal to 2g into 1 plus mu is the relation between the Young's modulus and rigidity modulus. Somewhat it is difficult, but you have to practice this equation, how to derive the relation between E and G. These are the two concepts involved in this equation to derive this equation. One concept is shear strain, the angular deformation, and second concept is the tensile stresses and the compressive stresses are acting on the diagonal. Due to that, tensile and compressive stresses on the perpendicular diagonals, the strain in the diagonal dB will be produced. Due to these two concepts, we can derive the equation between E and G. Clear, students? Let us go to the second case, the relation between E and K. In this case, in this session, we are going to derive the relation between E and K, that is Young's modulus and bulk modulus. Young's modulus is the ratio of linear stress to the linear strain. Bulk modulus is the ratio of direct stress to the volumetric strain. Let us consider a cube on which the stresses or forces acting on all three perpendicular directions in x, y, z directions, small p. Small p is the stress here, capital P is the load. Now consider a cubical element subjected to stress small p, stresses small p in three mutual perpendicular directions, x, y, z as shown in figure. In x direction, the stresses acting, and y direction is also stresses acting, and z direction is also stresses acting on that cube. Now stress P in x direction causes tensile strain. ఇప్పుడు ఇక్కడ అప్లై చేసే స్ట్రెస్ వల్ల ఆ లోడ్ వల్ల ఇది x డైరెక్షన్ లో దాని డైమెన్షన్ ఇంక్రీజ్ అవుతుంది. How much dimension will be increased? That is the P by E. This is the strain in x direction. Change in length by original length in x direction is equal to stress by Young's modulus is the strain in x direction. While the stress P in y and z directions, ఎప్పుడైతే మనం y డైరెక్షన్ లో z డైరెక్షన్ లో కూడా మనం స్ట్రెస్ అప్లై చేస్తామో ఈ రెండు స్ట్రెసెస్ వల్ల x డైరెక్షన్ లో దాని డైమెన్షన్ డిక్రీజ్ అవుతుంది. బికాస్ ఫర్ ఎగ్జాంపుల్ we stretches a wire or rubber band. If we stretches a rubber band, మనం అప్లై చేసిన లోడ్ డైరెక్షన్ లో రబ్బర్ బ్యాండ్ ఎక్స్టెండ్ అవుతుంది, దట్ ఈస్ ఇంక్రీజ్ అవుతుంది. అట్ ద సేమ్ టైం డయామీటర్ డిక్రీజ్ అవుతుంది. That rubber band diameter will be decreases by applying the force along the length. Like that, if you apply the load in one direction, the dimension, if you apply the tensile load in one direction, the dimension of the other direction is decreases. If we apply the load on the compressive load on the one direction, the dimension will be increased in the other direction. Lateral direction lo the dimensions increase decrease అవుతాయి ఒక డైరెక్షన్ లో లోడ్ అప్లై చేయడం వల్ల. రబ్బర్ బ్యాండ్ ఈజీగా అర్థమవుతుంది మీకు. రబ్బర్ బ్యాండ్ మనం పట్టుకొని లాగినప్పుడు ఏం జరుగుతుంది, దాని లెంత్ ఇంక్రీజ్ అవుతుంది. లెంత్ ఇంక్రీజ్ అయినప్పుడు దాని డయామీటర్ అబ్జర్వ్ చేయండి, డయామీటర్ డిక్రీజ్ అవుతుంది, చిన్నగా అవుతుంది, ఇజెంట్ ఇట్? అంటే డయామీటర్ డైరెక్షన్ లో దాని డైమెన్షన్ డిక్రీజ్ అవుతుంది. ఇక్కడ కూడా ఈ కేసులో కూడా ఈ y డైరెక్షన్ లో z డైరెక్షన్ లో అప్లై చేసే స్ట్రెసెస్ ఆర్ లోడ్స్ వల్ల x డైరెక్షన్ లో దాని డైమెన్షన్ డిక్రీజ్ అవుతుంది. y డైరెక్షన్ లో మనం ఇటు పట్టి లాగామనుకోండి, x డైరెక్షన్ లో దాని డైమెన్షన్ డిక్రీజ్ అవుతుంది. z డైరెక్షన్ లో కూడా మనం లోడ్ అప్లై చేస్తే x డైరెక్షన్ లో డిక్రీజ్ అవుతుంది. సో ఒక డైరెక్షన్ లో అప్లై చేసిన లోడ్ వల్ల ఇంకో డైరెక్షన్ లో దాని డైమెన్షన్ చేంజ్ అవుతుంది. ఇఫ్ ఇట్ ఈస్ టెన్సైల్, ఒక డైరెక్షన్ లో అప్లై చేసేది టెన్సైల్ లోడ్ అయితే దానికి పర్పెండిక్యులర్ ఉన్న డైరెక్షన్ లో దాని డైమెన్షన్ డిక్రీజ్ అవుతుంది. ఒక డైరెక్షన్ లో అప్లై చేసే లోడ్ కంప్రెసివ్ లోడ్ అయితే ఇంకో డైరెక్షన్ లో దాని పర్పెండిక్యులర్ గా ఉండే డైరెక్షన్ లో దాని డైమెన్షన్ ఇంక్రీజ్ అవుతుంది. సో అదే ఇక్కడ నేను సెంటెన్స్ లో రాశాను. నౌ ద స్ట్రెస్ P in x direction causes tensile strain P by E and in x direction, while the stress in P, that is the stress P in y and z direction, y and z direction లో అప్లై చేసే స్ట్రెసెస్ వల్ల డైరెక్షన్ కాజెస్ వాటి వల్ల ఏం జరుగుతుంది, కంప్రెసివ్ స్ట్రెయిన్స్. కంప్రెసివ్ స్ట్రెయిన్ represented in x direction is mu into P by E. P by E is the linear stress in y z directions into mu. We can multiply, if we multiply the Poisson's ratio, then we can get the lateral strain in x direction. Clear, students? If you understand the Poisson's ratio, it can be easily understand. Hence, strain in x direction, that is Ex is equal to x direction lo apply chese stress valla adi positive. Y and Z direction lo apply chese stress valla adi negative, because Y and Z direction lo tensile force apply cheyadam valla x direction lo dimension decrease avutundi kabatti the net change in dimension in x direction can be write in this formula. So strain in x direction is equal to P by E minus mu into P by E. Minus means they reduce the length in x direction due to stress in y direction. This minus represents, this minus represents reduce in length in x direction, reduce in dimension in x direction due to apply the load or stress in z direction. Yeah. From this equation, we can take it. The P by E is the common. The final equation is 1 minus 2 times mu. 1 minus 2 mu. P by E into 1 minus 2 mu. Ikkada P load kaadu, stress. Small p use chesanu. In some other books, it is represented by small p. Small p. In some other books, it is represented by sigma. Stress is represented by sigma or small p. If we note the capital P, it is the load. Load is represented by capital P. Stress is represented by small p. Similarly, in y direction, equation base cheskoni man y direction lo raskunte P by E into 1 minus 2 mu. Same equation y direction lo kuda ante strain jarugutundi, because three mutually perpendicular equal stresses are applying on the cube. Therefore, strain in x direction, strain in y direction, strain in z direction is also same, P by E into 1 minus 2 mu. These are the strains in three mutual perpendicular direction. Therefore, we can write the volumetric strain of the cube. What is the volumetric strain of the cube? Summation of strain in each direction, that is Ex plus Ey plus Ez, we can write as volumetric strain. So by summing of all three equations, we can, three are equal, therefore we can write as 3p by E into 1 minus 2 mu. This is the volumetric strain. From the bulk modulus definition, the definition from the bulk modulus is given as direct stress, that is the stress acting on the material divided by volumetric strain. What is the stress here acting in three mutual perpendicular directions? P. Direct stress by volumetric strain, direct stress divided by volumetric strain formula, 3p by, this is the formula, 3p by E into 1 minus 2 mu. P cancel. Therefore, E can be write as, if we write that equation as K is equal to, after cancelling the P, E divided by, E goes into the numerator, 3 into 1 minus 2 mu. That equation becomes like this. Dear students, from this equation, E equal to 3 into K into 1 minus 2 mu. So here E equal to 3K into 1 minus 2 mu. Take it as second equation. In the first previous case, we derived the relation between E and G. That is the E and G is equal to, once again I will write E and G relation. E is equal to 2G. There in first case we derived that 2G into 1 plus mu. This is the relation between E and G. Clear, students? Here the relation between E and K equal to 3K into 1 minus 2 mu. From these two equations, relation among E, G, K, we can derive the relation among three elastic constants. In first case, from the previous two cases, we know that in the first case, E equal to 2G into 1 plus mu we derived in the first case. In the second case, E equal to 3K into 1 minus mu, we derived it already. From these two equations, by eliminating mu between the above two equations, we can get the relation between E, G, K free from the term mu. If we eliminate the mu from these two equations, then we can get the relation among three elastic constants. From the equation A, this is the equation A, here I represented this as equation A and this is equation B. From the equation A, we can write as E by 2G minus 1, then mu equal to E by 2G minus 1 from this equation. So substituting in the equation B, by substituting this mu value into equation B, then E is equal to equation B becomes equation B. This is the equation B becomes E equal to 3k as it is. I written 1 into 1 minus 2 into in place of mu E by 2g minus 1, E by 2g minus 1. So 3k into 1 minus 2 into E by 2g, 2 to cancel, E by g remains minus into minus plus 2 into 1, 2. So plus 2. So 3k into 1 plus 2, 3 minus E by g. Clear, students? From this, 3k into 3 is the 9k minus 3k into E by g, 3k E by g. This is total is equal to E. Here, left hand side is E itself. So from this, 1 plus 3k, that is 9k is equal to 9k. From this equation, 9k is equal to, here E is there, E plus 3k by 3k E by g. E plus 3k E by g. 9k is equal to 3 E plus 3k E by g. E can be common. E can be taken as common. E into 1 plus 3k by g is the remains in the left hand side is equal to 9k. From this E equal to, so if we take the LCM, among these two parameters, g is the LCM, g LCM, then the equation becomes g plus 3k. G plus 3k is equal to 9k. Clear, students? Once again, you have to practice that mathematical equation. What is going on there? From the above equation, E is equal to, we can write as E is equal to, E numerator తీసుకొస్తే 9kg అవుతుంది. 9kg divided by this becomes the denominator in the right hand side, 3k plus g. Clear, students? E equal to 9 kg by g plus 3k, 3k plus g. So equation C may be expressed as, this equation can be expressed as equation C. This equation C. This is the equation C. This equation is also expressed as your 9 by E. 9 by E. This E it తీసుకొస్తే 9 by E. ఈ k it తీసుకొచ్చామనుకోండి gk. So gg cancel 1 by k plus kk cancel out 3 by g. Like that, 9 by E, there is a g plus 3k by kg. 9 by E, gg cancel, 1 by k remains here, and here kk cancel 3 by g. So 9 by E is equal to 3 by g plus 1 by k is the equation. Represents the relation among three elastic constants, Young's modulus. Young's modulus, this is the Young's modulus, rigidity modulus, bulk modulus. Clear, students? Let us go for worked examples on elastic constants. Two worked examples are there. One is the, I will explain one problem, and second one is you have to solve that. First example is, in a laboratory, a tensile test is conducted and Young's modulus of the material is found to be 2.1 into 10 to the power of 5. ఒక మెటీరియల్ పైన లాబొరేటరీలో టెస్ట్ చేస్తే యంగ్స్ మోడల్స్ ఎంత వచ్చిందంటే 2.1 into 10 to the power of 5 newtons per mm square. On the same material, torsion test is conducted. Another test is torsion test. That is, twisting test is also there in the laboratory to conduct torsion test. So on the same material, torsion test is conducted and the modulus of rigidity is found to be 0.78 into 10 to the power of 5 newtons per mm square. This is the E value, this is the G value. Modulus of rigidity or rigidity modulus is G value. Then determine the Poisson's ratio and bulk modulus of the material in terms of GPa. So ఇక్కడ మనం ఫైండ్ చేయాల్సింది ఏంటిది? Poisson's ratio and bulk modulus K value, capital K value. So this is the given data. K must be represented in GPa. You have to find the K in gigapascals. So we know that relations E equal to 2g into 1 plus mu. You have to remember these relations. Dear students, these relations. What is the relations we are derived up to here? E equal to 2g into 1 plus mu is the one of the relation between E and G, and E equal to 3k into 1 minus mu is the relation between E and K, and the relation among three elastic constants is E equal to 9 kg by 3k plus G, or 9 by E equal to 3 by k plus 1 by G. That is the relation among three elastic constants. These are the three equations you have to remember. So in this problem, E equal to 2g into 1 minus 1 plus mu is the relation among E and G we are using. E value is given 2.1 into 10 to the power of 5, and the G value is also given 2 into 0.78 into 10 to the power of 5 is the G value into 1 plus mu. So here we are going to calculate, or we can find the Poisson's ratio from the above equation as 0.346. Poisson's ratio is always less than 1 because it is the ratio of lateral strain by linear strain. Lateral strain is always less than the linear strain by applying the load on a material. Therefore, the Poisson's ratio is always less than 1. In this problem, the Poisson's ratio is 0.346 for a given material. Also, the relation we know that E equal to 3k into 1 minus 2 mu derived in the second case. E value 2.1 into 10 to the power of 5 is equal to 3 into k into 1 minus 2 into mu value is 0.346. From this equation, k is the only unknown. Therefore, bulk modulus of the material we can find it as 227.72 newtons per mm square, that is the megapascals. But in the problem, the bulk modulus is asked in GPa. If we convert this newtons per mm square or megapascal into GPa divided by 1000, therefore, if we divide the 1000 this value, then we can get 227.27 GPa. The bulk modulus of the given material is 227.27 material. Clear, students? This is the G value. 2.1 into 10 to the power of 5 newtons per mm square. This is the G value, that is the residual modulus 0.78 into 10 to the power of 5 newtons per mm square, and the bulk modulus value is 227.27. GPa is the answer. Second problem. In second example, a material has modulus of rigidity equal to 40 GPa. Modulus of rigidity means G value, capital G value, 40 GPa gigapascals, and bulk modulus equal to the 80 GPa. Bulk modulus means K, capital K is equal to 80 GPa. Then find the Young's modulus and Poisson's ratio. In this problem, we have to find the Young's modulus E value and Poisson's ratio mu. These are the answers. Try the relations between the E and GK and find the Young's modulus and Poisson's ratio. Clear, students? First of all, E and G are in this problem, G and K values are given. Find the Young's modulus and Poisson's ratio. You try it and solve it and check the answers. Another concept in this class we are going to discuss, that strain energy. It's the smallest topic in the MOS, strain energy. What is mean by strain energy? First of all, before going to the strain energy, we have to know that the energy stored in a body by applying the load. Any body, that is the energy stored in any body by applying the load on it. For example, if we apply the load on a rubber band, the work done taking place on the rubber band. మనం ఏం చేస్తున్నాం దాని మీద వర్క్ చేస్తున్నాం. Work done on the rubber band by the person when elongate the rubber band. ఆ వర్క్ డన్ ఏం జరుగుతుంది, మనం అప్లై చేసిన వర్క్ డన్ ఏం జరుగుతుంది, ఆ రబ్బర్ బ్యాండ్ లో స్టోర్ అవుతుంది. ఇజంట్ ఇట్? ఆ రబ్బర్ బ్యాండ్ లో ఎక్స్పాండ్ అయినప్పుడు స్టోర్ అవుతుంది. మళ్ళీ మనం లోడ్ రిలీజ్ చేసాం రబ్బర్ బ్యాండ్ మీద, రబ్బర్ బ్యాండ్ ఏం జరుగుతుంది, ఇట్ రిటైన్స్ ఇట్స్ ఒరిజినల్ షేప్. There is a regains its original shape. ఆ ఒరిజినల్ షేప్ రావడానికి దానిలో స్టోర్ అయ్యే ఎనర్జీని యూజ్ చేసుకొని ఒరిజినల్ షేప్ వస్తుంది రబ్బర్ బ్యాండ్. సో అలా ఏ స్టీల్ బాడీ అయినా ఏ ఐరన్ బాడీ అయినా మనం లోడ్ అప్లై చేసినప్పుడు అది ఎలాంగేట్ అవుతున్నప్పుడు దానిలో ఎనర్జీ స్టోర్ అవుతుంది. ఆ ఎనర్జీ స్టోరింగ్ నే స్ట్రెయిన్ ఎనర్జీ అంటామట. సింపుల్. ఫర్ ఎగ్జాంపుల్ స్ప్రింగ్ తీసుకోండి. స్ప్రింగ్ ని మన పట్టి ఆగితే ఏమవుతుంది, అది సాగుతుంది. సాగి దానిలో ఎనర్జీ స్టోర్ అవుతుంది. ఇఫ్ యూ రిలీజ్ ద లోడ్ అగైన్, the spring again comes back to the original position due to energy stored within the spring. ఆ స్ప్రింగ్ లో లోడ్ అయ్యే ఎనర్జీ వల్ల అది మళ్ళీ రిటర్న్ బ్యాక్ వచ్చేస్తుంది. ఆ స్టోర్ అయిన ఎనర్జీని స్ట్రెయిన్ ఎనర్జీ అంటాం. క్లియర్ స్టూడెంట్స్? స్ట్రెయిన్ ఎనర్జీ అంటే ఏంటి ఒకసారి చూద్దాం. Whenever some load is attached to a hanging wire, it expands and the load moves downwards by amount equal to the extension of the wire. Extension of the wire ఎంత మూవ్ చేస్తుంది, ఎంత ఎక్స్టెండ్ అవుతుందో అంత మూవ్ చేస్తుంది బాడీ లోడ్ అప్లై చేయడం వల్ల. A little consideration will be show that when the load moves downwards, ఒక వైర్ ని మనం హ్యాంగ్ చేసి లోడ్ అప్లై చేసినప్పుడు అదేం జరుగుతుంది, a little consideration will show that when the load moves downwards, లోడ్ కిందికి మూవ్ అవుతున్నప్పుడు it loses its potential energy. ఎప్పుడైతే మనం దానికి అటాచ్ చేసాం, వైర్ ఉన్న లోడ్ అటాచ్ చేసామో అది కిందికి మూవ్ అవుతుంటే దాని పొటెన్షియల్ ఎనర్జీ డిక్రీజ్ అవుతుంది, హైట్ డిక్రీజ్ అవుతుంది. కాబట్టి ఈ పొటెన్షియల్ ఎనర్జీ ఏమవుతుంది అంటే ద ఎనర్జీ అబ్జార్బ్డ్ వైర్ లో అబ్జార్బ్ అవుతుంది, స్టోర్ అవుతుంది. ఎనర్జీ స్టోర్డ్ ఇన్ ద స్ట్రెచ్డ్ వైర్ which may be released by moving the load. అది మళ్ళీ ఎప్పుడు రిలీజ్ అవుతుంది, మళ్ళీ ఆ లోడ్ రిమూవ్ చేసినప్పుడు రిలీజ్ అవుతుంది. ఆన్ రిమూవింగ్ ద లోడ్ ద వైర్ విల్ బి స్ప్రింగ్ బ్యాక్. ఆ వైర్ ఏమవుతుంది, ఒకసారి మనం లోడ్ అప్లై చేసి వదిలేస్తే ఆ వైర్ మళ్ళీ స్ప్రింగ్ బ్యాక్ వెళ్ళిపోతుంది టు ఇట్స్ ఒరిజినల్ పొజిషన్. దిస్ ఎనర్జీ విచ్ ఈ స్టోర్డ్ ఇన్ ఎ బాడీ, ఈ స్టోర్ అయిన బాడీ వెన్ స్ట్రెయిన్ విత్ ఇన్ ద ఎలాస్టిక్ లిమిట్, ఎలాస్టిక్ లిమిట్ లోపలే మనం ఆ లోడ్ అప్లై చేయాలి. ఎలాస్టిక్ లిమిట్ దాటితే ఏమవుతుంది, దాని ఒరిజినల్ షేప్ కి రాదు. ఓకేనా? విత్ ఇన్ ద ఎలాస్టిక్ లిమిట్ మనం లోడ్ అప్లై చేసినప్పుడు అది స్ట్రెచ్ అవుతుంది, ఎలాంగేట్ అవుతుంది. ఎలాంగేట్ అయినప్పుడు దానిలో లోడ్ అయిన ఎనర్జీని స్ట్రెయిన్ ఎనర్జీ, దానిలో స్టోర్ అయిన ఎనర్జీని స్ట్రెయిన్ ఎనర్జీ అంటాం. అర్థమైందా స్టూడెంట్స్? స్ట్రెయిన్ ఎనర్జీ అంటే ఏంటి, ద ఎనర్జీ స్టోర్డ్ విత్ ఇన్ ఎ బాడీ వెన్ ఇట్ ఈస్ స్ట్రెయిన్డ్ బై అప్లైయింగ్ ద లోడ్. It has been experimentally found that the strain energy is always capable to doing work. ఈ strain energy దేని వల్ల జరుగుతుంది, strain energy కొంత వర్క్ చేస్తుంది ఆ strain energy. So therefore work done is equal to strain energy. Mathematically strain energy can be represented by U, capital U, that is equal to work done. That is equal to work done means force into distance, force applied on the member into distance moved by the member. That is the force applied on the member is, if you apply the gradual load from 0 to maximum, the average load is half into P. If you apply the load P on the member from 0 to maximum P, gradual load, it is average load is taken as half into P. 0 plus P by 2, that is P by 2 is the average load. Deformation is delta. Distance moved by the member is delta. So half into, in place of P we can write as stress into area into, in place of deformation strain into length. So half into stress into area into length is we can get write as volume, area into length, and strain also can be write in terms of Young's modulus and stress. Strain can be replaced by sigma by E. Therefore equation becomes sigma into sigma, sigma square by 2 into E, sigma square by 2E into volume of the member. This is the strain energy formula. Sigma square by 2E into volume is the strain energy formula. Clear students? How to calculate the strain energy? Strain is sigma square, that is a stress square divided by 2E into volume of the member. Clear students? Another definition is there related to the strain energy, resilience. So this term is already read about this term in the MMS, Material Science and Metallurgy. Resilience. Resilience is the property of a material. It is the total strain energy stored in a body. When we applying the load on a body, how much total strain energy, that is the total energy stored in the body, is called as resilience. It is termed as resilience, total strain energy stored in the body. Sometimes the resilience is also defined as the capacity of strained body for doing work on the removal of straining force. ఎప్పుడైతే మనం లోడ్ రిమూవ్ చేస్తామో అది బ్యాక్ వెళ్ళిపోయే ఎనర్జీని రెసిలియన్స్ అంటాం. సమ్టైమ్స్ ఇట్స్ రిప్రజెంటెడ్ స్ప్రింగ్ బ్యాక్ ఎనర్జీ. సో రెసిలియన్స్ ఫార్ములా ఇస్ ఆల్సో ఈక్వల్ టు strain energy. Resilience antene total strain energy, that is formula sigma square by 2E into V. Clear students? Total strain energy ni resilience antam. Another definition, proof resilience. Proof resilience means the maximum strain energy which is stored in the body when it is elongate within the elastic limit. Only elastic limit varaki, ante elastic limit varaki మనం extend చేస్తే దానిలో స్టోర్ అయ్యే ఎనర్జీని ప్రూఫ్ రెసిలియన్స్ అంటాం. ఎలాస్టిక్ లిమిట్స్ వరకు కాకుండా బిలో ఎలాస్టిక్ లిమిట్స్ వరకు ఎక్స్టెండ్ చేస్తే టోటల్ స్ట్రెయిన్ ఎనర్జీ స్టోర్డ్ ఇన్ దట్ బాడీ ఇస్ రెసిలియన్స్ అవుతే, అప్ టు ఎలాస్టిక్ లిమిట్ వరకు ఎక్స్టెండ్ చేసినప్పుడు బాడీని స్ట్రెయిన్ చేసినప్పుడు దానిలో ఎనర్జీ స్టోర్ అవుతుంది. దట్ ఈస్ ద మాక్సిమం స్ట్రెయిన్ ఎనర్జీ స్టోర్డ్ ఇన్ ద బాడీ అప్ టు elastic limit is called the proof resilience. Proof resilience formula, in place of sigma you can write as it is replaced by sigma E. Why it is write as sigma E? Up to elastic limit, that is the stress up to elastic limit is represented by sigma E. Sigma E square by 2E into volume, the stress developed within the member up to elastic limit. This is a proof resilience formula. Next, modulus of resilience. Modulus of resilience means the proof resilience per unit volume. Every unit volume lo store aye proof resilience ni energy ni modulus of resilience anta. So modulus of resilience is equal to sigma E square by 2E. The volume cancel per unit volume by divided by volume cheste volume cancel avutundi. The remaining formula sigma E square by 2E is the modulus of resilience. All these three parameters are strain energies. Strain energies ఇవన్నీ మూడు కూడా, కాకపోతే ఒకటి per unit volume, ఒకటి up to elastic limit, ఒకటేమో total strain energy stored in the body. Clear students? This is the small concept. Next topic is strain energy in different types of loads. We have three types of loads. Strain energy in gradual load, strain energy in sudden load with impact, strain energy in sudden load without impact. These are the three cases we are going to consider. What is the strain energy stored in the bodies? First case, strain energy in the gradual load. If we apply the load on a material gradually from 0 to maximum, the strain energy formula already derived, that sigma square by 2E into volume. Sigma square by 2E into volume is the formula to calculate the strain energy in gradual load. Why? Because we are taking here half into P. Half into P. That means we are applying the gradually, and the load is varies from 0 to maximum. Maximum is P. Minimum is 0. Before applying the load, starting load is P. So gradual load lo manam gradual ga apply chesinappudu load varies from 0 to P value. So average load from starting to ending is P by 2. So in that case, half into P is the average load into deformation. From that equation we can get sigma square by 2E into V is the formula for strain energy in gradual load. Clear students? Here sigma stress is equal to load by area. Stress is equal to load by area for gradual load. Already we are using, that is we used this formula in many problems. Sigma is equal to load by area or resistance force per unit area. Then second case is strain energy in sudden load with impact. Suddenly apply cheste with impact, what is the energy stored within the body? What is the stress developed in the body? So this is the second case. Look at this diagram. This is the diagram. One bar is attaching at the roof, that is hanging at the roof, and at the bottom of that body we place one collar. This is called a collar. On that body we are releasing a load, some load P at a distance of height h from the collar. Dear students, కొంత లోడ్ ని మనం అంత హైట్ నుండి రిలీజ్ చేస్తున్నాం. ఈ కాలర్ పైన రిలీజ్ చేసినప్పుడు ఏమవుతుంది, ఈ లోడ్ వచ్చి దీనికి ఇంపాక్ట్ లోడ్ అప్లై అవుతుంది, సడన్ గా లోడ్ అప్లై అవుతుంది. ఓకేనా, ఇంపాక్ట్ లోడ్ ఆర్ ఇంపల్స్ లోడ్ అప్లై అయినప్పుడు ఈ మెంబర్ కొంత ఎక్స్టెండ్ అవుతుంది. దిస్ మచ్ ఆఫ్ ఎక్స్టెండెడ్, దిస్ ఇస్ ద కాలర్ ఆఫ్టర్ ద డిఫార్మేషన్. సో డెల్టా is the after deformation, the length of deformation is delta. What is the releasing height? H. H is the releasing height. Delta is the deformation of the body after the applying the sudden load. So in this case, strain energy is equal to work done. How much work is taking place by the load on the member? Work done is equal to force into distance. Force, how much force we are releasing? P is the load, force is releasing. Same formula. Here also we are going to take same formula. Strain energy is equal to sigma square by 2E into V. But stress is more in this case. What is the stress value here? stress value, strain energy is equal to work done, that is equal to load into distance moved. Load into distance moved, this is a strain energy. This can be equate to work done. Strain energy formula sigma square by 2E into V strain energy. Work done, here how much work is taking place by releasing the load P on the collar at a distance from the distance of height H is load into distance moved by the load. Distance moved by the load is load, initially the load is here, it is striking on the collar at a distance of height h, plus it is elongated up to delta. So total distance moved by the load is h plus delta. Load into distance moved is the work done. So P into h plus delta is the work done taking place by the load on the member. This work done can be equate to the strain energy, sigma square by 2E into AL. So sigma square by 2E into AL is equal to P into h plus delta can be replaced by sigma L by E. Delta ante it is extended length. Delta is equal to stress by Young's modulus into actual length. Dear students, so from this equation we can derive that, say, left hand side we sigma square by 2E into AL is equal to PH plus P sigma L by E. P is multiplied to both parameters. Divide the above equation on both sides by AL by E. Total equation is రెండు సైడ్ల AL by E తో divide చేస్తే then AL by E cancel అవుతుంది ఇక్కడ. The remaining parameter in the left hand side sigma square by 2 is equal to right hand side first parameter ని మనం AL by E తో divide చేస్తే EPH divided by AL plus ఈ ఈక్వేషన్ సెకండ్ పారామీటర్ ని మనం AL by E తో డివైడ్ చేసాం అనుకోండి, LL cancel, E cancel, A remains. So P sigma by A. So after dividing by AL, dividing the above equation by AL by A, the equation becomes sigma square by 2 equal to EPH by AL plus P sigma by A. So sigma square by 2 minus P sigma by A minus EPH by L equal to 0. Equation becomes like this. So therefore stress in impact loads, this is in the form of x square formula ఉంది, x square plus AX plus B, or AX square plus BX plus C is equal to 0. Clear, students? This equation is in the form of AX square plus BX plus C. AX square in place of A, 1 by 2 is there. 1 by 2 sigma x square A value, AX square plus BX plus C equal to 0 lo A equal to 1 by 2. In place of B, what is the value in place of B? Minus P by A. Minus P by A is there in place of B. So BX, AX square plus BX. X is the here sigma. Sigma is the X. In place of C, what is there? C equal to minus total value EPH by AL. EPH by AL is there in place of C. So ABC values, these are ABC values in the equation AX square plus BX plus C. So if we solve this equation, we can get X is equal to, or sigma is equal to minus B plus or minus root of B square plus 4AC. From that we can substitute in that equation sigma equal to minus B. Minus B means B value minus P by A, then minus B minus of minus plus P by A plus square root of P by that is B square. B square means minus P by A whole square, that is P by A whole square plus, sorry, minus here B square minus 4AC, minus 4AC, 4 into A 1 by 2, that is 4 into 1 by 2, 2. C value E minus EPH by L, therefore 2 into minus EPH by L, minus plus 2 EPH by AL. Clear, students? This is a sigma value. The stress in impact loads. Stress in impact loads with stress in sudden load with impact formula idi. Stress becomes this much. Third case, strain energy in sudden load without impact. Without impact means, for example, wire is there, load is applying from 0 to maximum. Here 0 to maximum apply cheste gradual load antam. ఒకేసారి కొంత హైట్ నుండి మనం లోడ్ అప్లై చేస్తే కొంత హైట్ నుండి లోడ్ మనం పడేస్తే దాన్ని ఇంపాక్ట్ లోడ్ అంటాం. ఫర్ ఎగ్జాంపుల్, one member is there, the load is placed on the member, suddenly the load is released on this member. Suddenly load is released on that member, then sudden load is applied without impact. Impact లేదు ఇక్కడ, పైనుండి మనం రిలీజ్ చేయట్లేదు, సింపుల్గా దాని మీద ప్లేస్ చేసి వదిలేసినప్పుడు ఏంటంటే దాన్ని సడన్ లోడ్ వితౌట్ ఇంపాక్ట్ అంటాం. ఇన్ దట్ కేస్ హైట్ వాల్యూ 0, మనం కొంత హైట్ నుండి మనం రిలీజ్ చేయట్లేదు కాబట్టి ఇక్కడ h is 0. సో ఇన్ ద above case we can place in place of h 0. So in place of h 0, this parameter becomes 0. So remaining parameter square root of p by a whole square. The square root of p by a whole square becomes p by a. So p by a plus p by a, 2p by a. The stress in the sudden load without impact is 2p by a. Stress in the sudden load with impact is this equation. Stress in the gradual load is p by a. Gradual load lo aithe stress ki manaki p by a form tha. Adhe sudden load with impact aithe this equation to calculate the stress, and sudden load without impact aithe stress ki formula 2p by a, and 2 times gradual load, 2 times the stress produced in the gradual load is equal to stress produced in the member due to sudden load without impact. These are the stresses induced in the 3 cases of loads: gradual load, sudden load with impact, sudden load. These are the 3 cases where we can easily solve the strain energy stored in the body by calculating the stresses. Clear, students? This is the topic in unit 1, and in, some more topic is there in the unit 1, the complex stresses. In the next class we are going to discuss about complex stresses.